First, I want to talk about the tremendous long-term benefits of competitive math. Students who participate in accelerated competitive math are simply going to have a huge academic edge over their classmates. Obviously, there are many subjects that involve arithmetic, algebra, or geometry and demand rapid computation. All the sciences, economics, statistics, computer programming, engineering, and students with high-level competitive math experience are just going to have a major time advantage when it comes to homework and testing over their peers, and this will last a lifetime. Competitive math also renders standardized testing a joke. The SAT, ACT, achievement tests, AP exams, you name it, they become very, very easy for students who have diligently trained for math competitions. And I can tell you that it definitely benefited me through high school, college, and into my professional career trading derivatives. Since math is a profoundly progressive subject where lessons build upon each other, competitive math has the added effect of really bolstering intellectual confidence. I can tell you firsthand that my confidence was through the roof directly as a result of all the math competitions I took part and excelled in, and consequently I developed a profound appreciation and love for mathematics. I would say that I have about as much competitive math experience as someone can possibly have. I competed prolifically throughout high school in numerous math competitions, timed exams, team events, mail-in contests, regional math meets. When I was in high school, the crowning achievement of my career was that I captained my high school's math team and I led it to winning the New England Championship, which was one of the most competitive leagues in the country. I also competed successfully on a national level in the American Regions Math League, and twice I was a high-scoring medalist for my team. I would also say that I am an extraordinary teacher. I taught the younger kids on my math team every single thing that I knew and learned, and as a result, a couple of them even went on to later surpass my own achievements. And over the last few years, I've been teaching my own kids math, and we've enjoyed extraordinary results. I would like you all now to watch these two videos of my children.
0. 2 times 8, 16. 8 times 7, 56. 5 times 3, 15. 5 times 2, 10. 5 times 7, 35. 9 times 7, 63. 3 times 0, 0. 5 times 6, 30.
Now sit up.
6 times 7, 42. 10 times 3, 30. 6 times 1, 6. 9 times 8, 72. 6 times 6, 36. 10 times 3, 30. 10 times 20. 9 times 7, 63. 4 times 9, 36. 2 times 8, 16. 5 times 2, 10. Is it wrong?
0 wrong?
Still wrong! I'm done! Woohoo! Look, no math writer anymore.
Good job, Chris.
Hi everybody, I'm going to show you how to solve a simple equation. 3x plus 7 equals 22. First, we subtract the 7 from both sides. 3x equals 22 minus 7. 3x equals 15. Now we divide both sides by 3. We get x equals 5. And to check we plug in x as 5. So 3 times 5 is 15, plus 7 is 22. So it's right. Hi everybody. Now we're going to solve another equation. 3x minus 10 equals 6. First, we add 10 to both sides to isolate the variable. 3x equals 16. Then we divide both sides by 3. And x equals 16 thirds. Which also equals 5 and a third. Now we check it. Let's see. 3 times 5 and a third, 15 plus 3 thirds, and 3 thirds is 1, so we get 16, and 16 minus 10 equals 6. So it's right. Hi everybody. Now we're going to solve another equation. 5x plus 8 equals 1. First, we subtract 8 from both sides to isolate the variable. 5x equals 1 minus 8. 5x equals negative 7. And then we divide both sides by 5 and get x equals negative 7 fifths. And in order to check it, we plug in negative 7 fifths as x, so 5 times negative 7 fifths equals negative 35 fifths, which divides to 7, negative 7, and negative 7 plus 8 equals 1. So it's right. Hi everybody. Here's another math equation. Negative 1/4 x plus 7 equals 2.5. First, we subtract 7 from both sides to isolate the variable. Negative 1/4 x equals 2.5 minus 7. Negative 1/4 x equals negative 4.5. Then we multiply both sides by negative 4 and we get x equals 18. Now we check our answer. We plug 18 in as x and get negative 18 fourths plus 7. And we get negative 9 halves plus 14 halves. And we get 5 halves which equals 2.5. And it checks out.
The absolute key to succeeding in doing well on math exams is what I call problem recognition. How quickly is a student going to look at a question, read it, completely understand what it's asking, and realize the best way to attack it? That's it. Again, I refer to this as problem recognition. And the only way to get better at problem recognition is to do more problems than your competitors. Speed. Speed is another crucial skill. People who do well on math competitions can add, multiply, subtract, divide, factor, solve and graph equations, you name it, they can do everything at lightning speed. And that comes, again, from simply doing the necessary preparation. Mistakes. Students have to eliminate mistakes. Again, these things are all tied together. A mathlete will make scores of mistakes in the course of their career. Stupid mistakes, silly mistakes, sloppy mistakes. But I staunchly believe there is a science to using scrap paper and knowing when to speed up, when to slow down, when to skip a question. And some of that comes with maturity and time, but most of it comes, again, from having done thousands of practice problems. Competition experience is also vital. If you just take one math exam per year, say the AMC, you're not going to be nearly as comfortable in a competitive math environment as a student who competes in several other competitions. And I know it's hard to find these competitions, and some schools might not even offer them. But that is something to keep in mind and work around if necessary. My math team coach was extremely resourceful. He entered us in every conceivable math competition, monthly mail-in exams, events we had to travel to. We did it all, and this ambition greatly contributed to our overall success level. There's a very simple formula for getting better at competitive math. You find the old exams, you do the old exams, you do every question multiple times, then you do them again. Students need to repeat this process until they can understand and explain the solutions to just about every question. Now, this will take some time and effort. There are many, many years worth of problems to go through and a lot of questions for each year. This approach, I would say, is a guaranteed formula for success. This is precisely how I trained, and the only other option one would have is to rely on natural or innate talent, which may take some select individuals pretty far, but the vast majority of students would greatly benefit from this more exhaustive approach. And I can say with the utmost confidence that the students who conquered the old exams will easily surpass the kids who may be theoretically smarter than them, but who haven't done nearly as much preparation. A student can't just haphazardly rifle through the old exams and solution sets on their own and expect to get maximum results. They've got to be a little more systematic. Kids need to learn how to solve the right problems in the right way. And what I mean by that is the problems they are working on should ideally be right at the frontier of their learning curve. They ought to be sufficiently challenging, but not too hard, too daunting, or too discouraging. And just because a student knows how to answer a particular question, that doesn't mean they have harvested all the educational value out of it. The method they used might be fraught with potential mistakes, and there might be a much simpler way to solve it. Again, in a time competition, they're going to have to learn the most efficient methods and solutions. And there is a real art to finding the next topic to study or the next question to tackle. You know, when a bright student is 9 years old, they might not have any idea that they should be learning about absolute value, the binomial tree, in circles, or something that they are more than ready for. And that's where the role of a mentor with vast competitive experience comes in. In the course of doing the old exams, they're going to hit roadblocks, and they're going to say, I have no idea how to do this. But that's telling them precisely what they need to work on. This might seem like common sense, but too many people veer away from topics that they think are obscure or unimportant, like complex numbers, trig, or analytic geometry, the stuff that seems harder. But I have my students move directly into that discomfort, and that's where they're going to focus. In fact, it's precisely in these thorny subject areas that they have the most opportunity to surpass their competitors. All right, let me tell you a little more about how I coach competitive math. First of all, lecturing. It doesn't work in schools, and it definitely doesn't work in competitive math. For the most part, my students work on problem sets and I stalk the back of the room, looking over shoulders and offering pointers. My lectures will only be short bursts of instruction. Again, the problem sets themselves are the main learning devices, not only because they pinpoint what the kids don't know how to do, but also because they can simulate the experience of timed competition. I'm a firm believer that everything a student uses in math must be proved. I can't tell you how many high-level math achievers I know who don't even know how to prove the area of a triangle is 1/2 base times height, never mind how to prove Stewart's theorem or how to derive trigonometric identities. However, if somebody knows where all the theorems and tricks come from, it not only prevents them from having to memorize formulas and relationships, it also produces a much deeper level of understanding, one which will serve them very well as the material gets increasingly more difficult. I'm a big believer in what I call math verbalization. Unfortunately, most math people, especially some of the most competent math people out there, cannot explain how they do their work. I submit that only when someone can teach and can articulate exactly what they're doing to others, only then have they truly conquered the material. Along the same lines as verbalization is the art and science of mental math. Adding, multiplying, subtracting, dividing, factoring, doing rapid computations completely in one's head. Mental math offers not only another dimension, another important skill that students in competitive math can really utilize and benefit from, but these cool mind tricks also never fail to excite whomever I teach them to. In my class, we do a lot of problem sets, and I offer individualized pointers. But the students are also going to get homework, and plenty of it. I have amassed nothing short of a mountain of old math competition exams from all across the country, so I'm able to give my students all the comprehensive and targeted assignments they will need to get really, really good at math. Again, there's no substitute for experience, and there is a finite stack of questions that ambitious students should go through. If they get through that, they will really take off. Far too many people out there mistakenly assume that math skills are innate, that a high level of math competence cannot be cultivated. I could not disagree with this more strongly, and I submit that my personal achievements have disproven it. Another grave mistake parents and teachers make is that they do not start their kids early enough. 3, 4, and 5-year-olds are fully capable of so much more than is generally expected of them. 5-year-olds can do algebra and geometry, 4-year-olds can multiply, and there's really no valid reason to hold these youngsters back. Paper and pencil sloppiness. This is something you won't hear anybody else talk about, especially institutional math teachers who are instructing 25 to 30 kids at a time. But I believe there is an optimal way to use paper and pencil, a singular approach that will help simplify rather than complicate the computations and problem sets at hand. I get right in there with my students, coaching every single pencil stroke, and I demand written clarity at all times. Insufficient geometry. The geometry on the AMC exams and at Scholastic Math Meets is far beyond what's found in conventional textbooks. And there's no way that anyone can simply figure this stuff out, no matter how smart they are. Ultimately, students are going to have to really focus on geometry if they want to do well in math competitions. And, more precisely, they're going to have to learn math competition geometry. Studying suboptimally. Too many kids will just grab a handful of old math exams, go through them, try a question, get stuck, flip to the solution, and nod their head and say, "I got it." But this is not at all the way to prepare, and I can guarantee you that they most likely don't have it. There's a proper way to attack these problems and a strategic way to deal with them when stuck. For the most part, it involves chewing on them for a long time and trying to figure them out without sneaking a peek at the given solution, even if it takes a long time. This really is the dirty work, the blood and sweat that leads to higher plateaus of math competence. So I'm a firm believer that there is an optimal way to prepare, and there are important subtleties to it. Boring curricula and boring teachers. Math, because of its progressive nature, is an exciting subject in its own right, and it's a shame that schools turn so many kids off from it. They do this in myriad ways, but the biggest culprits are poorly designed textbooks and exercises, and also the group learning environment itself, which tragically fails to challenge the smartest students. This is why competition math is so great. The people who write up these exams have put a ton of thought into them, and the questions are expertly designed and have elegant solutions. I'm going to leave you now with one more video of my son and star pupil.
Hi everybody. Today we're going to solve another quadratic equation. Consider the general case. ax squared plus bx plus c equals 0. First, we divide everything by a and move the constant term to the right side of the equation. We get x squared plus b over ax equals negative c over a. Then we look at the coefficient of x, which is b over a. We have it, which is b over 2a. We square it, which is b squared over 4a squared. And we add that number to both sides of the equation. Plus b squared over 4a squared plus b squared over 4a squared. This side of the equation factors into a perfect square. When we factor it, we get x plus b over 2a squared equals, now we look at this side of the equation. To combine it, we need common denominators. In order to make common denominators, we multiply top and bottom of negative c over a by 1 for a over 4a. So we get b squared minus 4ac all over 4a squared. Now we take the square root of both sides of the equation. We get x plus b over 2a equals the plus or minus square root of b squared minus 4ac all over 2a. Now, solving for x, we get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a.